Hello again. This is the course of data structures and algorithms. And in this video, I would like to explain about the shortest path. I guess some of you already have an idea to apply the shortest path in your team project. And this chapter will be a helpful lesson for you. So let's check what is the inside of the shortest path algorithm, and in particular I will explain the Dijkstra algorithm, and there are some other algorithms. Before I explain about the algorithm, I would like to explain about what is weighted graph and the shortest path algorithm itself, and some examples. Yeah, this is about the shortest path. In the graph section, we already learned that the graph is uh, graph is graph consists of node and edges. Okay? But most of the examples we had before, it was only a graph without a weight in the edge. So we have a weighted graph. A weighted graph means the edge has an associated numerical value. So we have a value to indicate something, for example, distance or cost or other things. Okay, and this is the example. It is about the flight route graph. So we already have many examples about this one, from Honolulu to San Francisco to LA and etc. So this graph represents the weight. This is the distance in miles. Okay. And we can figure out the shortest path. Uh, The shortest path problem is a kind of problem to find the minimum total weight. So we want to find the minimum total weight between two vertex with U and V, and we are given the weighted graph. So weighted graph is this one. The value of the edge between the two nodes, and we want to find what is the minimum total weight. The minimum total weight means the length of a path. Okay? So the length of a path is the sum of the weights of its edges. For example, if I want to go from Honolulu to maybe to Detroit, for example, okay, yeah, you can just calculate this number 2555. There is no option, but to the Detroit, you can use this route, or you can use this route. So you can go here and then here, or you can go here and then here, and then you can go here. So there are three alternatives, and you can you need to calculate what is the nearest. Yeah, so what is the shortest, because we want to find the minimum. That's if you want to check the longest one, like from the Honolulu to Providence, of course, you need to check many of the route, which is the minimum. Okay. There are many applications like the internet packing routine or the flight reservation, and for example, the driving direction. In the navigation, we want to find the shortest path, and of course, there are some uh, trade-off. For example, if you want to have a shortest path, you need to go to the highway and then you need to pay some money. But if you want to have a free way, then there might be some more time than the shortest path. Okay? So this kind of things you can do with the shortest path problem. And in the shortest path, there are at least two properties. Okay? So for the first is a subpath. A subpath, so you know about path in graph. A subpath of shortest path is itself a shortest path. Okay? So if there is a subpath, then a subpath of shortest path Of course, it is the shortest path itself. And the property number 2, there is a tree. Okay, there is a tree. You know, tree. We learn about the concept of tree. So there is a tree of shortest path from one vertex to other vertices. Okay. So this kind of tree, I guess, if you learn in the mathematical engineering, yeah, if you learn from the theory of set and the theory of graph for the first time, I guess you learn about the spanning tree. Okay, so we also learn about in the graph properties. We have graph spanning tree, and there are some famous algorithm for the spanning tree like Kruskal and Prism. I don't know if we have enough time. I can explain to you, but let's just see the possibility, and I will just explain the shortest path in this video. So if I want to go to Providence, yeah, then there might be a tree, and the tree is the shortest path from Providence. So you can use like the Kruskal algorithm to find the spanning tree from Honolulu to Providence, and you can use Kruskal, you can use Prism, then yeah, you can figure out what is the shortest path with that algorithm. Of course, there are many algorithms for the shortest path, but I do not want to discuss many. At least in this video, I will explain maybe the first. I will explain on two, which is Dijkstra and Bellman, and I will explain in the other video about the Floyd-Warshall. So Dijkstra algorithm is a shortest path from one node to all nodes. Okay, so that's the idea for the Dijkstra algorithm. But the Bellman-Ford, it also covers the shortest path from one node to all node with negative edges. Okay, so it's important to include the negative edges because sometimes it is not about the transportation. So it might be something related with cost. Okay, so if it is cost, if it is positive, then yeah, it means you need to pay some money. But if it is negative, then maybe you will get some money, you will gain some money. Okay, that's a kind of trade-off as well. And the Floyd-Warshall actually is a little bit different because the shortest path will try to find all pairs of vertices, and negative edges also allowed. So this kind of algorithm exists, and we will learn at least the basic one. So what is the Dijkstra algorithms? The Dijkstra algorithm, we want to find the distance. So the distance of a vertex V from a vertex S, it is the length of a shortest path between the S and V. Okay, so we want to find the shortest path between two nodes, and the Dijkstra algorithm computes the distances of all vertices from a given start vertex. So this algorithm, you need to set what is the starting point, and then you will explore for every node in the graph. The assumption is the graph is connected and the edges are undirected and the edge weights are non-negative. Okay, this is the key. Okay, when you have the Dijkstra algorithm, the edge weights are non-negative. Okay. In the process of Dijkstra algorithm, we will grow a cloud. Okay, a cloud, it means we have the vertices, and then we will begin with a vertex, like for example S, and eventually covering all the vertices. And we store with each of vertex V, and we want to put label dv. So let's say v means the value, okay? And it represents the distance of V from S. So it is the distance of that particular vertex from the starting point, and we want to put it on the cloud. For every step, we want to add to the cloud the vertex u outside the cloud with the label smallest distance du. So du means the smallest one, the smallest weighted graph to the vertex u. And after we find the smallest distance, we will update the label of the vertices adjacent to the vertex. Okay. So for example, we consider an edge E like u comma z. Okay. So we have this vertex u, and then we have this vertex z. Okay. And u is the vertex most recently added to the cloud. Okay. So this u is the recently added to the cloud, and z is not in the cloud. So I would like to find what is z. Okay. So the original z is 75. So yeah, maybe from this graph, like you can go here from this s to the u, and you have the z, and then from s you go to here, and then you go to the z, and yeah, original value we don't know which path has been taken, and the value is 75. But after we check, we want to know whether the 75, which is the original value of dz, will be compared with the du plus the value, the weighted in the edge between u and z. So we want to compare whether 75 and 50 plus 10. And yeah, we want to check the minimum. So the minimum value between 75 or 50 plus 10 between 60, it will be the new value of the z. So the dz will have a new value which is 60, because 60 is less than 75. So we want to find the minimum. Okay. So in this case, yeah, let's see from this iteration. Okay. So we want to start from A. So A is 0. Okay, because the value is, yeah, the original value is 0, and then we want to explore on every node. Okay, so for the exploration of every node, it means if I, yeah, the dz of A. Okay, let me just use dz. Okay. A will be 0, and then if I go from A to B, so we have the distance 8. Okay, because the weight of this edge is 8. And then if I go to C, then it will be 2. Okay, because the weight is 2. And then if I go to D, I will have the value of 4. Okay, so here is 4, 2 and 4. Now what about E and F? Yeah, we put the original value as infinite. Okay, because we still have not explored the node, and we have not explored the edge. Okay. So among the option like B, C, and D, we will choose the minimum. So the minimum is C. So we will explore next node, which is C. So the iteration 2, we will go to the C, and after we know that A is connected to C, so we explore again for all the respective node. Okay, so in the A, yeah, we still have the A to B. Okay, we have the value of 8. Okay, and then we want to check from C. Sorry, So we have this A to B again. We have the 8. And then if we want to go from A to B via Z, okay, so we have 2 plus 7. Okay, so 8 and 2 plus 7, which is the minimum? Yeah, of course, 8. Okay. So yeah, actually I need to put this one as 9. Okay, but yeah, the result is 8. So we will just keep 8. And then we have another possibility from A to D. Okay, so A to D, we have 2 plus 1. So it means the 3. Okay, and the original one was the distance from A to D, which is 4. Okay, so 4 compared to 3. Okay, 3 is the minimum. Then, yeah, later we will update about this one. What about E? Okay, E, we can achieve, we can go to E through C, because now we are connecting A and C. So the possibility going to E is through this way. So it means 2 plus 3, then we have 5. And then we can go to F, because we already reached C. So it means I have 2 plus 9, okay, and the result is 11. Okay, now we have all the new node. So we have 8 to, okay, because now we are in this A and C. So we choose the next minimum. What is the next minimum? We can get the, among the option 8, 3, 5, and 11. So 3 is the minimum. So we will go to T. Okay. So in the next iteration, we have A and C and D. So we will check again the value of each of the node. So we go from A to B. Yeah, if we go through ACB, so the result is 9. Okay, I didn't, maybe I need to update this one first. Okay. Yeah, I guess, yeah, you don't need to put this one because it is, yeah, if it is 9, okay, so there is no need to change to the 9 because we want to find the minimum. And after we know B is still 8, and then C is 2 because it is direct connected to C, and then D, what about D? Yeah, we have 3, which is the new updated value. So we will not consider this 4. Okay. And yeah, we go to E. E is still 2 plus 5. Okay. And what about F? So because we can go to this way, or we can go to this way, or we can go to this way. Okay, because we already said that the edge here is not the minimum, and this is the minimum, 2 plus 1, because it is the 3. So we want to compare now 2 plus 9, which is 11, whether it is minimum than the 2 plus 1 plus 5. Okay, 2 plus 1 plus 5 means 8. Okay, so we put the value 8 here. And then what about E? E, because yeah, we still have the root 2 plus 3, so it's 5, the same. Then yeah, we have the new value for E, yeah, the new value of F, which is 8. And we want to go to the next minimum, which is 5. So we go to E. Okay. So we explore A, C, D, E, and then we check. Now, if you go to B, okay, we have A to B, which is 8. And we go to B from A, C, B, which is 2 plus 7, which is 9. And there's a possibility to go to B through this one, 2 plus 3 plus 2. So it means 5 plus 2, 7. Oh, yeah, this is more short. Okay, this is shorter. Then I can just put the 7 into the new value for this node B. And then how about C? C is still the same, and then D is still the minimum, and E, now yeah, you can still have the same value, 2 plus 3, which is 5. And then F, okay, F, yeah, there is no other alternative, so we just have 2 plus 1 plus 5, and the result is 8. So after we have P, which is the minimum among the two, so P is 7 and F is 8, so we go to P. Okay, so we go to P, it means, yeah, there is no other alternative. Every node has been visited and we already find the minimum. And the last, yeah, we just visited the F. And F is still have the same value, which is 8. Yeah, then this is the result from the Dijkstra algorithm. So this is the algorithm. We did step by step by using the loop. So while Q is not empty, so we put the value return Q, remove minimum, and then yeah, we try to find the minimum among the two. If the value is the minimum, then we choose that value to replace the previous value. Okay. So in the Dijkstra algorithm, actually it is a graph operations, and we want to find all the incident edges for each vertex. And the label operation, it sets the distance and locator label of vertex Z. Okay, and yeah, we want to find the time complexity. Okay, so the time complexity refers to the O degree of Z. So it depends on the number of the nodes in the particular vertex. And for the setting or getting a label, it takes only O1, yeah, because we just get one label, or we just get one vertex. We can use the priority queue. Do you still remember the priority queue? Okay. Sorry. So in the priority queue, you can set the value. Okay? So the value means that you want to priority the vertex which has the minimum one. Okay? So with the priority queue operations, you can insert into and remove ones from the priority queue, and it takes log n. Okay? And the key of a vertex in the priority queue is modified at most degree W. So it's the degree of a vertex, and each key change takes O log n. So yeah, when you want to change, it's all related with the sorting actually. So later we will do some more things with the sorting, especially if we have the value and we want to just do the sorting inside of the particular list. And the Dijkstra algorithms, so based on this operation, the label operation and the priority queue operation, then we can just say that we will explore for all the n, it means for all the nodes, and for all the edges, which is m, and we have the log n because we want to check which vertex is having priority. Then yeah, we can check that the result is somehow like n plus m log n according to these properties. And the running time, so you can express it with m log n since the graph is connected. Okay, so this is the worst case. Okay, so n plus m is somehow yeah, you can say why just consider m, because m is more important in order to do the priority. So the m plus n, yeah, yeah, you can say something like the properties on a graph we can check from the degree. Okay, you know the degree of v. Okay? The degree of v means, yeah, you want to find all the edges of a particular node, and the summation of all the degree of v, or it is respective to the n. Yeah? So we can just say it is like 2m. Yeah? So this is from the graph property. Then we have like 2m plus m. Okay? When we have this one with log n. Okay, okay, this is the parenthesis, and yeah, we have like 3m log n. Okay, and we know that in the big O notation, you can just omit the particular coefficient, so you just have m log n. Okay, so that's the idea why the Dijkstra algorithm just take m log n. So this is the implementation. I will explain this implementation, I think, in the next video. And the Dijkstra algorithms actually was based on the greedy method. Yeah? You know what is greedy method? Greedy method means you want to find the minimum. You want to find the minimum. You want to find the minimum, and you want to explore every node. Okay. Suppose it didn't find all shortest distance. So let f is the first wrong vertex. Okay, so let's say I just found any vertex, but it was wrong. So you can check when we find the p. Okay, okay. So it was wrong at the first time because it always take it the 8, but actually we can go here. Okay. So we can also see from D. Okay, D we have the 4 like this one, but this root is more. This root is shorter. Okay, so we can say that the edge was relaxed. Okay, so when the edge is relaxed, yeah, of course, now we want to explore any possibility to that particular node, and the distance cannot be wrong, so there is no wrong vertex. Okay, but the problem is when we have a negative edge. Okay? The negative edge is not possible with the Dijkstra algorithm, because when you find the best root for a particular node, for example, you go to E, 6 plus 0 is 5, 6 plus 0, oh, yeah, this one is a new one. Okay, so it's not the same with the previous example. For example, yeah, we want to go to C because we have 6, yeah, and you want to find the shortest path, so we have an alternative 4 and 1, so we have 5, and then we have another root to E, which is 5 plus 0, so the result is 5. And we go to F, here we have the 4 and 5, which is 9, and we have 4 plus 1, which is 5, minus 8. Okay, we have this minus 8. Okay. Yeah, in this case, we already said that this is the best one. Okay, 4 plus 1 is the best one, and yeah, there is option whether you want to choose the 5 or you want to choose the minus 8. But we already say that this is already the true value. Okay, and if you want to go to this part, okay, you need to choose whether you want to go this or you want to go this. And yeah, this is another things in Dijkstra. If you consider this one, it means, yeah, we can have the 5 minus 8, so it will be minus 3. But actually, yeah, you will do the other way. Okay, so let me. The problem now, if you have this 4 plus 1, 4 plus 1 is 5. Okay, but if you go from this direction, 4 plus 5, which is 9, and then 9, you go to this root, it will take minus 8, and the result will be 1. So which do you choose? You want to choose 5 from this root, or 1 from this to this to this? So in Dijkstra, when you find the minimum, you will set that one as the first one. So if you have the negative, you will not cover it. That's one of the issues with the Dijkstra. So we can use another algorithm, which is the Bellman-Ford. Okay. So the Bellman-Ford is something about the shortest path with negative weight. Okay, when you do with Dijkstra, it is not allowed to have a negative, but with the Bellman-Ford, it is allowed to have the negative. And you need to assume that it directed edges. Okay, so the directed edges means you have the direction. And the iteration I find all the shortest path that uses I edges, and the running time will be n multiplied by m, because we want to explore for every node and for every edges, and it will be all the possibility can be extended to detect a negative weight cycle if it exists. Okay, so let's see. I think I don't need to explain this one. I guess, yeah, you can read this by yourself. So I will explain with this kind of example. Now, suppose we have the starting point, which is A. Okay, so we have A, and then we have the direction. Okay, in the Dijkstra, we assume that it is undirected, but in the Bellman-Ford, we assume that it is directed. And let's say we have A, and then its starting point is 0, and every node will have infinite. And then we want to explore A to B, A to C, A to D. So the B will have 8 of the value because of this 8, and then C will have minus 2 because of this 8, and then D will have 4 because of this 8. Okay, so we will choose the minimum one again. Yeah, we can see this one as the minimum, minus 2. So we will explore from C. So from C, we'll explore the other nodes. Okay, so for example, we want to go to P. So minus 2 plus 7, then it means 5. Yeah, now we are updating the P to 5. And then from C, we can go to E. So it is minus 2 plus 3. And before we do this one, actually in the Bellman-Ford, we can just explore from C to P and then P to E. Okay, so this root is first. So we have the 5 and a plus minus 2, so it is 3, and then we have the minus 2 plus 3, so the result is 1. Okay, we want to find the minimum. Oh, why it is 6? I guess it should be 3, I guess. Yeah. Oh, yeah. And okay, the other part of the node from C is going to D. If the D first was 4, and then we have the minus 2 plus 1, so the result will be minus 1. And then from C to F, okay, we have 9 of the original, but we can have because now we are still on the C, we can explore later from the D which is 1 plus 5, it will be 6. So yeah, first we just set the from C, and we know that the minimum, more like the possibility, like 5, 1, 6, and -1 and 9. So the minimum was the minimum is -1. So we will explore for the next node, which is D. So the D, now we have the node here. Oh, okay, maybe the color. I didn't change the color here. So the B is still 5, and then C is -2, and then D is -1, and E is 1, okay, because of the node from C, -2 plus 3, so it's 1. And then what about F? So F, if we visit D, then we have the alternative. So the D is -1, and -1 plus 5, it is 4. So there's a kind of relaxing with the edge. Okay, if you want to go to F through this node, it will be 4. Okay, but if you go to F through the other node, okay, because it is a directed, it's not undirected, so there's no option to go to F without going from this way. So if we go to F, then yeah, it's the last one. There is another kind of algorithm we call it DAG. Okay, DAG based algorithm. It means I want to perform the similar way like the Bellman-Ford, but I will use topological order. So it works with negative weighted, but you want to use the topological order. The topological order means you need to set the edge. You need to set the vertex based on the A, B, C, D. Okay. So if it is from the previous example in the Bellman-Ford, you just use the minimum one. But for this example, we are just considering what is the next after A. So yeah, for example, after A is B, then you will use B. What is next after B? C, then you will go to C. Okay. So it's much faster than Dijkstra algorithm, and yeah, the running time is somehow like O(n plus m). Okay. So n means this is the number of nodes in topological order. So we already sort that one, and after we sort, we want to check for all the edges. So all the edges in the particular node, on the particular node U, then yeah, you need to find the distance. So the result will be n plus m, because the maximum is m according to the value of the edges. Again, let's see, I will change a little bit. So we have A, and then now it's B is here, C is here, D is here, E is here, and F is here. So we want to set the order as the A, B, C, D, E, F. So after we have the A, we go to all the possibility. Again, like the breadth first search, but we will choose the minimum, and yeah, we go to the next topological, which is B. Okay. And we go to B, and then we explore what is the possibility of the nodes after B. So there's C, and then F, and then E, and then D. Okay, and you need to check this node. Okay, you need to check the direction. Okay, the direction, because of this direction, yeah, you can check that B can go to C, B can go to F, B can go to E, B can go to D. Okay, and after you have those values, yeah, we will go to C, and then we will go from D to check the other possibility. Okay, so this kind of mechanism is much faster than the Dijkstra, and it allows the negative weighted. Okay, I think this is all for the video about the shortest path, and on the next video we will learn other things about the Floyd Warshall algorithm. See you on the next video.